let him in when he gets here. Let's talk about, let me turn this music off. Let's talk about Edpuzzle, not to, oh, I got to unfreeze. Not to yell at you or get mad, or just, I want to show you what I see and what it's reporting. And if we have issues, we're going to take care of it. So I forgot to delete people from last year. So like Morgan, she's in college now. So some of these are, but here's what it says. So pretty good to start out the year. Very good. So some of you haven't watched it yet. So you would get a 0 on this, and then if you watch it later, you'll get the points back. Sarah's gone. So some of these are old names that I got to delete out of here. So that's what I see. Ellie's gone. Some of these are last year. So that's who it says watched. Any issues or comments or questions on that? All right, so that's Edpuzzle. That's what I get to see. And we're here. I got to delete the ink out of this from last period. I printed this out for you. Away we go. Two, three, four. There you go, bud. 6, 3, 4, 5, 6. 6 here. Hopefully our distance learning student will, oh, here we go. Participating, very good. Continuous, let's start at the top here. Objective students will be able to evaluate limits and graph piecewise functions. Oh, we got the Khan video. He does a nice job. So let's kind of introduce it with that. I don't know if I still have it open or not. I think I do. Go back up, up. Thank you. Turn the sound up. I'm going to apologize in advance if I don't turn that down and I turn the music on. It's going to make you pee your pants a little bit. It's shocking. So I try to remember to turn that down.
So here we have the graph. Y is equal to g of x. We have a little point discontinuity right over here at x is equal to 7. And what we want to do is figure out what is the limit of g of x as x approaches 7.
Now keep in mind when he talks about this, when you approach a value, you don't really approach from a mile away. And actually approaching this from 6 is really far away, really far. A lot can happen between 6 and 7. But it's as far as introducing this topic, that's not a bad way to talk about it.
So essentially we say, well, what is the function approaching as the inputs in the function are approaching 7? Let's see. So if we input as the input to the function approaches 7 from values less than 7. So if x is 3, g of 3 is here. G of 3 is right there. G of 4 is right there. G of 5 is right there. G of 6 looks like it's a little bit more than or a little bit less than -1. G of 6.5 looks like it's around -0.5. G of -6.9 is right over there. Looks like it's a little bit less than 0. G of -6.999 looks like it's a little bit, it's still less than 0.
See how he's talking about 6.9999, 6.9999999. We want to approach it really close to see what's happening there.
It's a little bit closer to 0. So it looks like we're getting closer as x gets closer and closer, but not quite at 7. It looks like the value of our function is approaching 0. Let's see if that's also true for x values greater than 7. So g of 9 is up here, it's around 6.
We don't approach values from a mile away, but it's not a bad way to talk about it. I'm not criticizing him, and he knows that. He knows that we approach very closely, but this is a nice way to introduce it.
G of 8 looks a little bit more than 2. G of 7.5 looks a little bit more than 1. G of 7.1 looks a little bit more than 0. G of 7.1 looks like it's a little bit more than 0. G of 7.01 is even closer to 0. G of 7.000001 looks like.
Hear him say that? 7.00001. What happens when you're getting extremely close to this point? What are the y values going to? And as you get to 7.00001, I'm sure it's getting very close to 0.0001, just slightly above 0.
It will be even closer to 0. So once again, it looks like we are approaching 0 as x approaches 7. In this case, as we approach the larger values of 7. And this is interesting because the limit as x approaches 7 of g of x is different than the function's actual value, g of 7, when we actually input 7 into the function. When we actually input 7 into the function, we can see the graph tells us that the value of the function is equal to 3.
Now what that's saying is if your limit and your function value are different, there must be a discontinuity there. Somehow we're approaching 0, but when we get there, that point's been removed. That's called removable discontinuity.
So we actually have this point discontinuity, or sometimes called removable discontinuity, right? And this is, I'm not going to go a lot of depth here, but this is starting to touch on how one of the ways that we can actually test for continuity is if the limit as we approach a value is not the same as the actual value of the function at that point, well, then we're probably talking about, or actually we are talking about a discontinuity.
All right, cool. Good job. All right, so speaking of discontinuities, let's talk about some discontinuities. But we're going to first talk about just a nice continuous curve. So let's say we have two. Oh.
Approaches -3. If we just look at x equals -3, it's really hard.
What about continuous curve? What if our curve just went to here, to this point, and to this point right there? If I said, prove that this function is continuous at the point 2, 3, you can't just point to it and go, well, see, there's a point there. You say that the limit as x approaches 2 of f of x is equal to 3, and not only is the function approaching that point, when it gets there, it's actually 3. So on a calculus test, that's how you prove continuity. Or we can use a similar fashion to prove discontinuity. So let's look at removable discontinuity. What if we had the same point? Same type of curve, except right there, and maybe -4, that's down there. What if we had this situation here? We would say that the limit as x approaches 2 of the function is still equal to 3. It's approaching 3. This function is in no way approaching -4 at all. But when we get there, f of 2 is equal to -4. So this is a removable situation. If we could just fill in that one point, we would remove the discontinuity. Jump to maybe 3, -4. What if our function did this? Maybe a solid dot there and an open dot there. There's certainly a jump discontinuity. Now what would that look like? Well, we would say that the limit as x approaches 2 does not exist, because in order for the limit to exist, the left-hand limit and the right-hand limit need to be exactly the same. They're not. The left-hand limit is 3, right-hand limit is -4. There's no limit there. Now, f of 2 is equal to 3. It still has a function value. It's where that solid dot is. I'm kind of encroaching on space here. Infinite discontinuity. Let's say at 2, we've got a vertical asymptote and the curve looked like this. Now the left-hand limit is infinity, and the right-hand limit at 2 would be infinity. But we say that the limit as x approaches 2 of f of x, that does not exist. And you're like, well, you just told me that if they're the same, then it has a limit, with the exception of infinity. Infinities are not necessarily the same. In this case, they're not. Not only that, if you have an infinite discontinuity, f of 2 doesn't exist either. There's a vertical asymptote happening there. So neither exist. Don't worry about infinite oscillating. It never comes up. Questions? Am I good to go? Looks like I am. All right. Determine the limit by substitution. Support graphically. We don't ever really support graphically. Sometimes you can just plug values in. In other words, what you're finding out is this function just continuous there? Is it just nice? And usually on an AP test, I mean, this hardly ever happens. This would be definitely a free point. It's usually some other situation that we're looking at, of course. Okay, let's try the same thing here. We got 1 plus 2 minus 3 over 1 minus 1. So I just plug the value in, plug 1 in. 3 minus 3 is 0 over 0. We can't divide by 0, and we still can't do 0 over 0, but we have this situation. It's called an indeterminate form. In second semester, we'll investigate indeterminate forms a lot more. There's lots of indeterminate forms. This is one of them. But if I take 1 and plug it into the function, and I get 0 over 0, there's only one factor where I plug 1 in and I get 0. That's x minus 1. So what happened is there must be an x minus 1 on the top, and we see that x minus 1 on the bottom. What's the other factor? X plus 3, that's right. Now those cancel out. Remember, go back to your graphing. When you have those factors cancel out, what's happening there? Do you remember? On the graph. Not an asymptote, good guess. Asymptote is what makes the denominator 0 unless they're canceling out. There's a hole in the graph there. So if we take what's left over and plug that in, the hole is at the point 1, 4. So the limit, what is it approaching? It's approaching a y value of 4. So this is actually a line, x plus 3, y-intercept of 3, with the hole at 1, 4. And that's what's actually happening there. Of course, you don't have to do all that. You don't have to end up graphing it, but I'm just telling you what's happening there. Why is it a limit of 4? Well, that's where the hole is. If I plug 0 into this, we get square root of 0 minus 1. We get square root of negative 1. So for your homework, limit doesn't exist. But let's take it a little, now you don't have to do this in your homework, but let's take it a little farther and let's examine why this is happening. Here's the parent function, here's square root of x, very roughly. What happens when you minus 1 on the inside of a function? What does that do to the parent? Minus 1 on the inside. It goes right 1, doesn't it? It goes right 1. Reflecting it would be like a negative on the outside. So this got pushed over 1. Well, we're being asked what's happening as x approaches 0. Remember, we're on this function right here. Well, it doesn't exist over here. It doesn't exist over at 0. This graph is not, it has nothing at 0. We can only imagine what's happening at 0. Hence the term imaginary numbers, right? If we could imagine what's happening, it'd be the square root of negative 1. It'd be I. But that's only in the imaginary world. We're not living in the imaginary world for limits. So that's why we just put does not exist. And of course, for your homework, you don't need all that. You just need to tell me it doesn't exist there. Graph doesn't exist there. How are we going to talk about the limit? All right. You don't have to do this for your homework for greatest integer function either. However, I think this really shows you what's going on, especially on your one-sided limits. You might want to have this graph handy. Greatest integer function means the biggest integer not bigger than the one you're evaluating. So the greatest integer function of 0.1 is 0. The biggest integer not bigger than 0.1 is 0. So anything between 0 and 1 will just be 0. Open dot on 1 because when you get to 1, it becomes 1. Anything between 1 and 2 is 1. 1.3, 1.4, 1.5. The greatest integer of all those values is 1 because you can't go over. It's like the Price is Right. Can't go over. So it's this infinite step function. There's an infinite amount of discontinuities on this graph, which is kind of cool. But what about negatives? What's the greatest integer of negative 0.3? What's the biggest integer not bigger? Negative 1, isn't it? Is 0 bigger than negative 0.3? Yep, it's bigger. Can't have that. So that's down here. The greatest integer of negative 1.4 is negative 2. Like that. So what's the limit as x approaches 3.7? No problem, it's 3. If you're in the middle, it's just going to be 3. If you're at the integers, now you got a problem. The limit of the greatest integer of 2 from the left. 2 from the left is 1. Limit as x approaches 2 from the right of the greatest integer is 2. And what does that tell you? Well, there's no limit at 2 because the one-side limits don't equal each other. What is the limit as x approaches negative 4.3? Be careful now. So biggest integer not bigger than that would be -5, right? -5. Be careful with negatives. Try the first one. No big mystery on the first one. This is certainly not a calculus level question. Is 0. So the answer is 0. Oh, by the way, let me get your attention, please. Let me get your attention. I don't want this to be tricky. If this would have been 0 over 5, the limit is 0. If this would have been 5 over 0, the limit does not exist. In order to go, oh, there's a hole in the graph, it's got to be 0 over 0, because that means those factors canceled. This doesn't exist because we're talking about that vertical asymptote. So the only time you have an indeterminate form is when it has to be 0 over 0. And that leads us to this one right here. This is 0 over 0. So what is one of the factors on top? What has to be one of the factors on top? X minus 1, right? Has to be X minus 1. So that's a little bit of a clue on how to factor the difference of two cubes. Remember, same, opposite, always plus. It's the SOAP. I don't know if you ever heard that. I'm sure you have. Same sign, opposite sign, always plus. So now when we get 0 over 0, the limit still could exist. X squared plus X plus 1. So this is a parabola, and the whole is at, let's see, 1 squared is 1 plus 1 plus 1. The whole is at 3. So the whole is at 1, 3. And it's a parabola, but the limit is just simply 3. All right, nothing down there. I like this graph. This graph is kind of cool. If we plug 0 in, we get 0 over 0. Now that is an indeterminate form, but in this case, the limit does not actually exist. Sometimes it does, but this is not a case where we have a hole in the graph. We actually have a jump discontinuity at 0. If I plug in 1, I get 1 over 1. Plug in 2, I get 2 over 2. 3 over 3, 4 over 4, and so on. So those are all 1. Open dot. Anything to the right is going to be 1. If we plug in -1, the absolute value makes it 1. So we get 1 over -1, 2 over -2, 3 over -3, 4 over -4. Those are all negative ones. And, the top will always be positive, but now the denominator will be negative. Notice that we did have an indeterminate form, but at 0, we don't actually have a limit. It's not a case where it's just removable or a hole in the graph. So the questions you'll probably see, and I'm probably giving away an assignment question here. The limit is x approaches 0 from the right of f of x is we're approaching a value of 1. So the answer is 1 there. We're approaching 1. Now, when we get there, it doesn't exist, but when we get there, that goes from being a limit to being a function value. When we get there, now we're talking function values. limit as x approaches 0 from the left is down there at -1. And that's why we don't have a limit at that point. But we still have a right and a left limit. That's no problem. Explain why you cannot use substitution to determine the limit. Find the limit that exists. 1 over 0. Function does not exist there. In this particular case, we have a vertical asymptote. That's why the limit doesn't exist there for that particular one. What's the limit as x approaches 0 of sine of x over x? I asked you to memorize that. What is it? It's 1. That's right. It's 1. If we investigate the graph for this, up here at 1, there's a hole in the graph. And the graph looks like this, which is kind of a cool little graph. There is an asymptote at y equals 0. This is an asymptote because the graph is getting closer and closer and closer. The amplitude of the curve is getting smaller and smaller and smaller. The y values are approaching 0, but they're oscillating. They're going positive, negative, positive, negative, positive, negative. And that causes that graph to cross that asymptote, that horizontal asymptote, an infinite amount of times. You can cross horizontal asymptotes. You just can't cross vertical asymptotes because by definition, the function doesn't exist there. Doesn't have a function value. So to solve this one, we're going to use that. We're going to use the fact that that's 1. And I call it reverse common denominator. I mean, it's still common denominator, but it's backwards. We're splitting it back up. X over x plus sine of x over x. That's completely legal in Nebraska to do that. Common denominator. But now, the limit of the sum is the same as the sum of the limits. X over x is 1, plus limit as x approaches 0, sine of x over x. The limit of the sums is the same as the sum of the limits. Well, the limit of a constant is just 1, and we were told that this all equals 1. So the answer we're looking for on that one is just simply 2. Any questions? All right, finally. Our other goal for today is to be able to graph piecewise functions. Calculus loves piecewise functions, and I'll give you a calculus question when we're done here. This is the left side, this is the middle side, that's the right side. So from negative infinity to 0, it looks like a parabola. So if I plug 0 in, 0 plus 1 is 0. Open dot because there's not an equal on that part. Negative 1 is 2. Negative 2 is 1, 2, 3, 4, 5. Negative 3 is 10. So here's on the left side of our graph, the far left side, from negative infinity to 0. 0 to 2 is a line. We're calculus students. You can graph a line any way you want. I don't care how you graph a line, just get the job done. More specifically, a line segment. We plug 0 in, we get 3. 1, 2, 3. There's your y-intercept. Slope of 1, up 1 over 1, up 1 over 1. There's our little line segment. There's the middle part. Not necessarily the middle of the coordinate system, but the middle of our graph. And then to the right side, it's all 4s. So starting at 2, 1, 2, 3, 4, like that. Now that's certainly not calculus. what's calculus about this is if we found the limit as x approaches 2 from the left, what would 2 from the left be? Five. Right here. We're going from the left to 2. That's up here at 5. So the limit as x approaches 2 from the right, there's your 4. And you're like, whoa, 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 whoa. I thought there's an open dot there. How can it be approaching 4? It's approaching 4. It's not 4 when it gets there. A function value is different than a limit because f of 2 is equal to 5. We know that. There's the solid dot. Limits and function values can be the same thing on a continuous function, but not necessarily. It's two different questions. All right. Whew. Boy, I love this. I love this. This is awesome. I could talk about that all day, but I digress. I wish this wouldn't come down. No, that's not what I wanted. Oh, I hit stop share. I want to continue to share. Share, go. There we go. No. No. Eli's sitting there going, what is he doing? Period 4, there's your assignment right there. It's also listed right here. Here's the assignment. This is what you want to bookmark. This is the page you'll use a lot. And I have it linked to your Google Classroom right there. This should actually, can I move that? Yeah. That should actually be up there. There we go. $11:55. You need to be back in your seat by 12:28. When we get back, we'll have 10 minutes. That's not 10 minutes of sit and do nothing. I'm telling you right now, that's not what it means. You can put your stuff away with 2 minutes left in the class, so we're looking at 36. Okay, there's another issue that I need to talk about. When they fogged this room during lunch, and I had some papers sitting out, and the custodian said, those papers might get a little wet. So what I would do, I would just close your Chromebook, put anything paper like your notebook and your notes, I would just throw those in your bag when we go to lunch so nothing's getting wet. And it's just a mist. It's a very light mist. So I think if the top of these Chromebooks get misted, I just don't see an issue with it. If you're worried about that, then throw everything in your bag before you leave. I don't think you really have to take your bag. I don't think you're going to come back and see a wet bag. I don't think that's an issue. But if you're worried about any of your stuff, I'd put it away before we leave. Well, you gotta work out your 7 now, though, right? We don't leave till 55. That should be done before class.
It looks like you have a capital L somewhere. Do you have Larry somewhere else? Oh, you need help with Java. Yeah, you get every file has to be .java. That might be. Oh yeah, it works. There we go. I don't know why it's not hearing your console.
Yeah. Yeah, it's in the class information. That should be in the Google Classroom. Click on class information. It's right in there. Nope, time. All right. Mezzanine.
Well, just saying, you're telling me what's going on, why she's here, big hour.
It's not wet here. We're very responsible. Yep. People as we yeah. There's cameras. So they got secret cameras in here. So why are we like working tomorrow? It's like wait, where go? Yeah. Cancel it. Going off. Some hard. Yeah. Cancel that. This kid's had a 2 good for so long.
All right, you can please get settled in and get some homework done. I know it's only 10 minutes, but hey, it's 10 minutes of stuff that you get done. I'd appreciate it. Anybody get the school lunch today? Nobody did? How'd it go? Did it go all right? Yeah.